Yeah, good morning to all of you. In today's class, we are discussing about fundamentals of MOSFET. Let's have a quick review what we have covered in the last class. Okay, so last class you can see we have covered separating the signal and the DC quantities. We have discussed, in an amplifier circuit, there are two components. One is a DC component, other is an AC component, or called signal component. The voltages and currents that we see in an amplifier circuit has got both the components. We have shown here few examples here how base emitter voltage has got both DC component and an AC component. Okay, so even the collector current also, it has got both DC collector current and AC collector current. Like this we can keep writing, for an amplifier circuit the all voltages and current in terms of DC component and the signal component. And we have shown even the amplifier circuit which is an AC amplifier circuit, okay, which has got only the AC components here, and related currents and voltages we expressed in different forms here. Following this, we have discussed hybrid pi model, which is a simplest model and very popular model for the bipolar junction transistor. So using this how to design or develop this model, we have shown that. And here we have a NPN transistor, which is a bipolar junction transistor. The equivalent of that is shown here with the help of two components within that. One is the R pi and the resistance, which is measured between base and emitter, looking into the base terminal of a transistor, and there is a current source, a dependent current source, okay, whose magnitude is Gm times Vbe, that's flowing from collector to the emitter. The magnitude of this is given by Gm times Vbe, and the current flowing here depends on the base emitter voltage, okay, applied between the base and emitter terminals here. So this is version 1 of hybrid pi model, which is generally used for small signal operation of the BJT. Likewise, we have derived even the related expressions for the hybrid pi model. Then we have expressed the same model in alternative way in terms of the base current. So you can see here the current source here is a dependent current source whose magnitude is now beta IB. We have shown that how we arrived at that expression. We expressed collector current in terms of beta and base current here. That's how we have another model for BJT. The first model is based on voltage controlled current source, VCCS, whereas the second model, or version 2, okay, our second version of hybrid pi model is based on current controlled current source. As you can see here, this is a current source which is controlled by the input current here, base current here, since the current flowing in this current source is beta times IB here. So these are the two different versions of hybrid pi models we have discussed, and we finally arrived at a few observations. The first observation is going to be the models predict the operation of the BJT, and the model parameters like Gm and R pi, they depend on the DC bias currents. We have shown that through mathematical expressions as well, and model is applicable for both NPN and PNP transistors without any change in the polarities here. So these are the things that we have discussed in the last class. With that, I think we have come to an end of further related topics related to the MOSFET. And if there are any questions, I can take up before we proceed to the MOSFETs. Any questions are there? Okay, so by this time you should be familiar with the bipolar junction transistor. The fundamentals, even though we don't cover here, our syllabus starts from BJT biasing, and then followed with the small signal operation and models. Okay, basically for an amplifier circuit. Similarly, here we start with the MOSFETs and a few biasing circuits. Then we proceed to the small signal operation and the modeling of MOSFET here. So prior to the covering this biasing in MOS amplifier circuits, I thought let me cover a few for MOSFET fundamentals, and later on we can jump into the different bias circuits which are used in amplifier MOS amplifier circuit. So that's why we in today's class I spend this class particularly dedicated to the MOSFET fundamentals. Okay. Alright, let me move on to the MOSFET fundamentals. Okay, look at here, everybody is aware of what is MOSFET. Okay, so MOSFET, MOSFET. MOSFET stands for metal oxide semiconductor field effect transistor. As you can see here, this can be separated into two segments. One is MOS, the other one is going to be the FETs. Just to show it in a different color. Okay, so these are the two keywords which you can see here. The first, let me highlight here, what do we mean by MOS? How do we got this keyword MOS? And equivalently we have another important keyword is FET. If you look at this, this MOS stands for metal oxide and semiconductor. So M stands for metal oxide and there is a semiconductor. If we observe a physical structure of the device MOSFET, we will come across these three different layers here. On top we have a metal, and at the bottom we have a semiconductor. The metal and semiconductor layers are sandwiched with silicon dioxide, which is an excellent insulator here. So based on the physical device structure, this name has been given. So that's why the name is metal oxide semiconductor. Other side, if you look at the field effect transistor here, so this is based on the operation of the device. So if you look at physical operation of this the MOSFET device, so it works on the the principle of the field effect here. Okay, so we will see what do we mean by field effect. So FET here stands for field effect transistor. Okay, so this is an expansion of MOSFET. Together we can call metal oxide semiconductor field effect transistor. That's the name MOSFET stands for here. So let us go in detail here. MOSFET is a 3-terminal device, semiconductor device, as you can see here, and that can be used in different applications. Applications which range different applications we have. That if you look at the variety of applications of MOSFET, 99.99% all electronic system uses MOSFET as a fundamental or basic device in that. Okay, in them electronic systems especially. So we applications range from signal amplification, which is an amplifier, to the digital logic and memory. Variety of electronic systems, as you can see in all those systems, it employs the fundamental device as a MOSFET here. You may ask a question here, why we don't use a BJT. So from fabrication point of view, BJT is not good. Of course, the BJT has got some important even properties also. Switching speed, when it comes to switching speed, BJTs are good in switching speed, whereas when it comes to fabrication and the cost of fabrication, the MOSFET stands first. Okay, so that's the definition of what do we mean by MOSFET. Let's look into the basic principle here. What we use, what is the basic principle of operation of all three terminal devices. Though we have shown here this basic principle related to the MOSFET here, this is generally applicable for all three terminal devices here. So, the basic principle involved in the MOSFET is the use of voltage between the two terminals to control the current flowing in the third terminal here. I advise students to join at before 8:45. If you join late, I may not able to permit you. It disturbs the class also. Okay, so I was discussing, this is a basic principle used in the operation of the MOSFET. The same principle is also applicable for BJT as well. Okay, so what do you mean by that? So we are applying the voltage between the two terminals. You can see this word. Okay, so we are applying voltage between the two terminals. This in turn controls the current in the third terminal here. So this is, as you can see in the sample switch I have shown here. The switch behavior, the MOSFET behaves like a switch here. There are two terminals, you can see here. The one is connected to the power supply, which is labeled as VDD, and another terminal is connected to the ground. There is a control terminal, which is, you can see here, which is a with reference to MOSFET, this is usually a gate, and this is going to be the drain, and this is a source. Now you can see here the current flow between the supply to ground is controlled by this gate terminal here. Okay, so that is the basic principle of operation of the MOSFET. Usually current flows from supply to ground. The current flowing from supply to ground, you can make it a zero value, or we can make it a very large value also. That all depends on the gate terminal here. Okay, so this is the basic principle used in the even BJT and as well as MOSFET here. So now let us see the different transistor types, as we already discussed more about bipolar junction transistor. So now it's a time to look into the metal oxide semiconductor field effect transistors. Okay, why MOSFETs are so popular? So MOSFETs are popular in the design of integrated circuits, which are the circuits fabricated on single silicon chip. The main reason for the popularity of MOSFET is because of their usage in the fabrication of the integrated circuits. We can pack the millions and billions of MOSFETs in the IC version, in the integrated circuit form, which is nothing but a single silicon chip which houses billions of the transistors, which can be used for variety of the functions. So that's how the MOSFET has become very popular. When it comes to BJT, it's very difficult to fabricate them on integrated circuits, and cost involved in BJT fabrication is very high. That's the reason behind why BJT was not become so popular in the electronic era. So the MOSFETs are so popular because of this usage in the integrated circuits. Now let's have a few comparison between the BJT versus the MOSFETs. So even though I highlight here only with reference to MOSFET, so that means the advantages of MOSFETs here. The other way it's going to be the you can think of the disadvantages of BJT as well. So look at the first advantage of MOSFET. MOSFET requires a small area on single integrated circuit chip. Okay, compared to the BJT, MOSFET occupies very little area in the single IC chip, or single silicon chip here. That's the advantage for us. Okay, so that's why we see a very compatible or handheld the electronic device nowadays, because of this MOSFET occupies very little area, and so many MOSFETs can be packed in a single silicon chip. And look at the manufacturing process. Manufacturing of MOSFET is relatively simple compared to the BJT. Too many processes are involved in the BJT manufacturing, so that's why it's a tedious, and moreover cost involved is very high. And look at the operation of the MOSFETs here. So MOSFET operation requires very little power. Okay, so small amount of power is required, as we said here. Gate is used to control the current movement, current flow from the drain terminal to the source terminal here. This control current, if you look at, it's going to be very, very small, negligible amount of current. The typical value of current that this MOSFET takes is 10 to the power of minus 15, which is negligible amperes of current here, to control the current flow from supply to the ground here, compared to the BJT here. So that's the meaning of this. Okay, if you look at from power consumption point of view, the operation of the MOSFET consumes very little power for its operations here. Okay. MOSFETs can be used to realize both analog and digital functions as well, and they can be used both for amplifier design, PLLs, okay, op amp. In variety of the analog circuits, MOSFETs can be used, and also for digital functions, MOSFETs can be used to realize logic gates such as AND gate, OR gate, NOT gate, XOR gate, and so many digital logic functions like multiplexers, okay, so encoders, decoders, okay, the flip flops, everything can be implemented using the MOSFETs here. So MOSFETs in general can be used to realize both analog and digital functions here. And nowadays you come across a situation where in which you can see both analog function, analog blocks, and digital blocks in a single silicon chip. So, if you look at an IC, some part we dedicated it for analog, and some part we dedicate for digital here. So these kind of ICs are called as mixed signal ICs here, okay, where they deal with both analog signals and as well as digital signals. Okay. So now let us look into the other advantages of MOSFETs. More number of MOSFETs can be packed in an IC. Typically it is a billions of MOSFETs. Such a chip is called as VLSI chip, very large scale integration chip. Okay, since area occupied is very small, more number of MOSFETs can be packed in a single silicon chip. Nowadays we call this with alternate name called gigascale integration, GSI. Okay, so the other equivalent names exist in the literature also. Okay, so we'll move on to the types of MOSFETs. So we have seen the advantages of MOSFET over BJT. Now let us see the different types of MOSFET and its physical structure. MOSFETs are generally of two types. One is N-channel, N-type or N-channel type MOSFET, as you can see here. The channel here, a conducting region, is of N-type, that's why it is an N-channel MOSFET. Another one is going to be the P-channel MOSFET here. There is a conducting channel between the two different regions. Okay, so that type of channel is P-channel here. So based on the conducting channel between the source and drain, we have a different types of MOSFETs here. And let's look at specifically to the N-channel MOSFET. So N-channel MOSFET again further can be divided into two different types, enhancement type and depletion type here. So enhancement type has positive voltages, okay, and the characteristics falls in the first quadrant, okay, since they have since N-channel enhancement type transistor has voltages and currents which are positive, so therefore the characteristics falls in the first quadrant. Whereas the depletion type transistor, okay, so here the voltages and currents that we deal here are negative, therefore the characteristics falls in the third quadrant here, since both are going to be negative here. Okay, so N-channel here, if you look at the popularity of these two, among these two, so enhancement type transistors are most widely used in all the analog and digital functions compared to the depletion type MOSFETs here. Okay, if we study any one type of MOSFET, then other type of MOSFETs can be easily understood. So our focus is mainly on the enhancement type MOSFET. We'll try to explain the details of enhancement type MOSFET, so that students can go back and even try to understand the other different types of MOSFETs like N-channel depletion, P-channel enhancement, and P-channel depletion type MOSFETs here. So I strongly suggest you students to go through these two types of MOSFETs, N-channel enhancement type MOSFET and P-channel enhancement type MOSFET. Reason would be in CMOS, which is a complementary metal oxide semiconductor, we will see both type of devices like N-channel enhancement, let us call as NMOS, and this P-channel enhancement, let us call as PMOS. So therefore within a single silicon chip of CMOS, it houses both N-channel enhancement type MOSFET and P-channel enhancement type MOSFET. So that's how so if you become familiar, so it becomes easy for us to understand more about the CMOS device. So current state of the art technology is CMOS. Maybe 50 to 20 years back we were using only NMOS technology, and prior to that we were using PMOS technology. and now the technology has integrated both NMOS and PMOS together. So that's a CMOS technology. So you see both analog functions and digital functions realized based on CMOS instead of only NMOS and PMOS. To moving further, we have N-channel enhancement type MOSFET. The physical structure from perspective view, as you can see here. Okay, so this is the three-dimensional structure of N-channel enhancement type MOSFET. Let us try to understand each of these regions here. This is a since it's a three-dimensional view, you can see each and every layer, and its depth also can be seen very easily here. First and foremost, I would like to show the terminals here. We have a source here, as you can see here. We have a source here, and we have a drain here, and we have a gate here, and at the below we have a body or bulk. Okay, so this is though we say MOSFET is a three-terminal device. In fact, if you look at more detail, MOSFET is a four-terminal device. The most of the times, the body terminal or bulk terminal B is suppressed because we short circuit source and body or source and bulk. So therefore, we ignore the fourth terminal here. Commonly used terminals are source, gate, and drain. Okay, and gate region you can see here. It's made up of metal region here, and between metal and at the bottom you can see there is a substrate here. This region is substrate here, as you can see here. This is a substrate region here, and since we are discussing here N-channel enhancement type MOSFET here, the substrate you can see the type of substrate here. So it's going to be the P-type substrate, which we call here as a body. Okay, so this is a body P-type substrate here. Okay, so within the P-type substrate we add two regions here. One is source region, as I am showing here. This is the source region here. Two regions, N plus regions, are diffused. N plus region. N plus stands for here heavily doped. We write it like this, N plus, which is heavily doped. So two N plus regions exist within the P-type substrate, as you can see here in 3D view. This is completely, it is an N plus region. This is N plus region, and the same here also you can see this is an N plus region here. Okay, and at the bottom we have a P-type substrate here. In general, MOSFET has got P-type substrate and two N plus regions, which are one of the region we will call as source region, and other region we will call as a drain region here. Okay, in between covering these two regions, source region and the drain region, we are going to deposit a silicon dioxide here. As you can see, this is small horizontal lines here. Okay, that shows it is silicon dioxide here. Okay, which is labeled here. You can see here. Okay, so this is silicon dioxide, which is an insulator here. On top of that silicon dioxide, we have a block color thick, thin, not thick, it is a thin layer. So this is called as a metal. So now for the metal we attach an electrode which is a gate here. Okay, and even for the this drain region we deposit a metal and attach terminal to that. Likewise, even you see here for the source region also we deposit a metal and attach a terminal to that. Wherever we want terminal, we deposit metal here. So this metal nowadays it is called as a polysilicon here. This is a polysilicon. Okay, earlier we were using aluminium as a metal. Okay, but now in place of metal we use polysilicon. This can be expanded as polycrystalline silicon here, and the reason is the aluminium the melting point is somewhat different from the silicon. Therefore, to match with the processing for MOSFET, we use silicon as a conductor. So that's why this silicon as a conductor is nothing but it's a polysilicon. The silicon, which is a poly, is made in the form of polycrystalline silicon. This behaves like a conductor. So therefore we use in place of metal, okay, so the polysilicon is acts like a metal here. So we can detach, can attach a terminal to electrode to this. So this is the 3 terminal, the 3D view of the MOSFETs here. Okay, so go through this. If you have any questions you can ask related to this. And another important thing is the dimensions here. As you can see, the channel length here, this is called as a channel. The distance between the source region here and the drain region, okay, that distance we call as a channel. Okay, from here till here we denote that with the capital L. So that is called as a channel region, because here the charge carriers keep flowing here when we apply suitable potential to the gate here. So this region is a channel region here, and this length of this channel region is denoted as capital L. And the width of the channel you can see here, this is a W. So this L and W plays a very important role in the MOSFET design. Okay, usually the IC designers, they try to minimize the length, and sometimes we maintain width as a constant, so that we can get more high speed, we can design high speed MOSFETs by designing this smaller L here. Current state of the art is it's nanometer technology. Okay, so earlier in 1980s we have seen the technology L is called as a technology, or feature size what we call. Okay, so though our textbook that we are discussing is a micrometer, describes designs in micrometer, but currently the state of the art technology is in nanometer. That means in each and every MOSFET that we use in today's mobile phones, or laptops, or any digital computers, the distance between the source region to the drain region is going to be in nanometer. Coming days, even this may even get miniature, because of we want to achieve higher speed, and for that the only solution is minimize the channel region here. So by minimizing channel region, so electrons traveling from source to drain, they take less time here, and lesser the time we get more current or more number of charge carriers can flow when we reduce this distance here. Okay, the cross sectional view of this MOSFET can be seen below, as you can see here. Same thing when you cut it into the slice, we see here the cross sectional view. So this gives a few details what we are seeing here get suppressed here, because this is only the cross sectional view. In most of the textbook we show the cross sectional view instead of showing you the perspective view or 3D view. So cross sectional view is for theoretical understanding, so this becomes easier. Here you can see the few informations that we are unable to see there, especially the thickness. Okay, here we can't show the thickness of silicon dioxide, but now you can see thickness is TOX, which is this is silicon dioxide thickness is shown here, and all the things what we have discussed here are once again you can see here also. There are source terminal, gate, drain terminal, body terminal, there is a p-type substrate, and there is a channel region here, this distance between source and drain region here. Okay, so now the electrons cannot move from source region to the drain region, because these two are isolated due to the p-type substrate region in between them. So this is just type of semiconductor is opposite to that of source and drain region, therefore current cannot flow. Charge carriers can only flow from source region to drain region when we have similar material here, similar region here in the channel space. We want to have here some region like n-type here, so that if I create some n-type region here, so that the charge carriers can move from here to here. Okay, so we will see that how that works, how to create a channel, and how this device works. We will see here. With that, I think you have understood now the both physical structure of a device, okay, MOSFET device, n-channel enhancement device. Okay, and later on we will see that how to use this device, the physical operation of a device. Before that, let me go through the points related to the physical structure. Figure 1 is applicable to the perspective view, okay, and cross sectional view, referring to those figures which shows physical structure of the n channel enhancement type MOSFET. I'll go through quickly all these points here. So anything which is left out, that students can follow here. The transistor is fabricated on p-type substrate, which is a single crystal silicon wafer that provide physical support for the device and for the entire circuit in the case of integrated circuits here. So this is what I am talking here. The p-type substrate, this acts like a foundation for the entire circuit. And if you look at wafer, so this is one portion of single silicon wafer. So wafer looks like a circular like this. Okay, this is a slice of wafer, and here we, to make ICs, we cut them into the slices like this. Okay, and this each square sized portion here is an integrated circuit here. So this is an IC. Okay, usually in a silicon wafer like this, or in an ICs like, we fabricate similar ICs here. Okay, this IC may be an Pentium computer or Pentium processor. Okay, so similar ICs we fabricate on the entire wafer here. So now this substrate, what we are seeing here, the foundation material of the silicon wafer is nothing but it's a p-type substrate. So on top of that, we diffuse with n-type source and n plus drain regions here. That's what I was referring here, because now the substrate what I have shown here provides a physical support for the device and the entire circuit of an ICs here. Now the third thing is, what is important is, two heavily doped n-type regions indicated as n plus source region and n plus drain regions are created in the substrate, as we have shown here. These are the n plus source region, n plus drain regions. These are heavily doped because it's rich in the charge carriers. They are deposited on the top of this substrate here. Okay, let me show here. On top of this substrate, what you are seeing, p-type substrate, we see here two n plus regions here. That's what this point shows here. A thin layer of silicon dioxide of thickness typically 2 to 50 nanometer. As you can see, the silicon dioxide is very thin, which is in terms of 1 nanometer. When we compare this with the source region and drain region, the depth is very large, but here silicon dioxide thickness is very small. The reason why we make thin silicon or thickness of in terms of 2 to 50 nanometer, a very thin layer of silicon dioxide is to have a very good control of the charge movement here. This, with reference to this I am talking here, this silicon dioxide is going to be around in terms of nanometer, few nanometer, which is 2 to 50 nanometer in thickness. Reason why we make this as a thin is because we will have very good control of charge carriers in the channel region. Okay, so to have a good control here, we make this layer as very thin. Okay, that's the reason here, which is grown on the surface of substrate, covering both source and drain regions here. So we will deposit silicon dioxide such that the source and drain regions are covered. And next, on top of that, we have a metal is deposited on top of the oxide layer to form the gate electrode, as we have seen that already in the physical structure. Metal contacts are also made to the source region and the drain region, and as well as substrate regions. Wherever we need an electrode, we attach metal. Metal, as I told you, it's usually a polysilicon, okay, in current VLSI fabrication. So these are the various terminals we have seen that. Now in general, we have MOSFET is a 4-terminal device which has got gate terminal, source terminal, which we show it as a capital G, capital S, capital D, and the last one is going to be the substrate or body terminal, which we have shown with capital B. Now why the name is apparent as MOS is also discussed here. The name of the device is derived from its physical structure, as I told already, because of this 3 layers, metal, oxide and semiconductor, which are quite apparent when you see the physical structure here. As you can see, this is a top is a metal, the black color shaded region is a metal, and below we have slant lines that is shown is silicon dioxide, and next we have a substrate region which is a semiconductor here. So, 3 regions are very in term, it's like a silicon dioxide gets sandwiched between the metal and the semiconductor. That's why the name is a metal oxide semiconductor here. That's why the name has become apparent because of that. There is another name for the MOSFET which is also called as Insulated Gate Fet, or shortly we can call that as IGFET. This is because of the physical structure of the device, emphasizing the fact that gate electrode is electrically isolated from the device body. And gate current, as already told you, it's going to be very small, which is 10 to the power of minus 15 ampere here. That's the magnitude of gate current here. So this device MOSFET consumes little gate current to allow minimum or maximum current between the source and drain. Now we can see we can think of MOSFET. Inside MOSFET there is a PN junction. We will show that where exactly the PN junction. The substrate form PN junction with the source region and as well as even drain region also. In normal operation, these junctions are kept reverse biased at all times. Let us go back to the device and see where these PN junctions can be seen within the MOSFET. This is very important when we want to understand more details about the MOSFET. So, as you can see, this region is N plus here, this is N plus region. There is another N plus region which is here, as you can see I am highlighting here. This is another N plus region, and look at the type of substrate here. The substrate is of a P type here, which we are calling as just as a body. Now this forms a PN junction, right? There is N plus here and P type substrate here. This looks like a PN junction here. Let me show the PN junction here. A diode like this, and there is even one more diode here like this. So P type is the substrate here. I would like to write here. This is a diode what we are seeing here. So in this, the PN junction formed here in the source region, the N plus region acts like a source, and this substrate region acts like a anode here. So this is a P type substrate. Likewise, we have even another diode at the drain region. Okay, whereas this is again P type substrate. This is same as this, and here we have other side we have a drain region. Okay, so this kind of PN junctions can be seen within the PN junction. Sometimes we call this as parasitic elements here, because they reside in another device which is in this case it is a MOSFET here. And during the normal operation, what it happens here, they remain the turn off at all times, because in normal operations we know that we keep a drain at positive voltage, okay, with reference to source. Okay, so here we tie this to the positive voltage, and look at what happens when we connect drain to the positive voltage. Okay, when drain is kept positive voltage, obviously this becomes reverse biased. This diode PN junction becomes reverse biased, and again here also you can see that with reference to the source, we short circuit this source and the body. So therefore this device becomes PN junctions becomes inactive during the normal operations here. Okay, that's what we are trying to explain here. Okay, so kept reverse biased at all times during the normal operations here. The reason is discussed below. The drain will be at positive voltage relative to the source, and the two PN junctions can be effectively cut off simply connecting substrate terminal to the source terminal. We short circuit substrate and source terminal, because as I told you we generally use 3 terminals. Substrate terminal will get short circuit with source terminal. Let me show that here. So this terminal I am talking here. Generally we short circuit this source to the substrate here, and so that we don't use this body terminal here. Now we apply all voltages with reference to the source. we see, for example, gate source voltage we apply between gate and source, that only two voltages here which we need to understand. One is VGS, other is VDS. So VGS is nothing but voltage applied between gate and source. This is the control voltage that creates channel here. We will see what kind of gate source voltage creates channel between the two regions here, source and drain regions respectively. Another voltage which is required for the electrons to move in the channel region in a longitudinal direction, horizontal direction, is VDS. Okay, so here the VDS is the voltage applied between the drain and source here. That means all voltages within the MOSFET are applied with reference to source. Another way we can say that it is applied with reference to body or bulk substrate here, since these are short circuited here. I don't want to deal with what happens to the device when we apply some voltage between the source and substrate, and that's not the scope of this the topic. When we go to the more details, then we will see the consequence of applying voltage between the source and the body also. Okay, so those things, these are the two voltages which students has to be familiar with, so that you understand the other things like currents very easily here. And only current here that is very important is going to be the drain current here, that flows from drain terminal to the source terminal here. So there is a drain current. Sometimes we call this as IDS also. ID or IDS both are same, because the gate current is very small, 10 to the power of minus 15 ampere. This current can be neglected because there is an isolation because of there is silicon dioxide which isolates this gate from the substrate here. So this current is Ig. In reality we will make it as 0. It's negligible current here, very less. For an ideal device, Ig is going to be 0. For a practical device, it's going to be 10 to the power of minus 15 amperes. So those are the currents and voltages which we need to be familiar. Next is the substrate has no effect on the device operation. Since we are short circuiting substrate and the source terminal, the substrate doesn't have any effect on the device operation. This implies that MOSFET is a 3-terminal device, namely gate, source and drain. The voltage applied to the gate controls current flow between the source and drain. This current will be in a longitudinal direction from drain to source in the region labeled as channel region here. When we apply suitable voltage at the gate, let me show this with reference to device here. When we apply suitable voltage between the drain and the source, positive to the drain and the negative to the source. Okay, so what happens, let us see here. And also we need to apply voltage between the gate and source. This acts like a control. This drain to source voltage will create a current flow here, because having applied this VGS creates a channel here, and here we need to apply positive gate voltage. Applying here positive gate voltage, as you can see, this looks like a capacitor because there is a top is a metal and below there is a substrate. This looks like a parallel plate capacitor. Positive gate voltage applied here creates negative charges here. All holes will get repelled, holes will move away like this. Okay, all holes will move away like this, leaving the negative charges here. All negative charges will accumulate near silicon dioxide. Negative charges cannot cross and go to the gate because there is a insulator here. So therefore all negative charges accumulate near the silicon dioxide. So this is called as a channel region here. These negative charges forms a path between the source and drain region here. Now once we apply drain source voltage here, this causes the electron to move from source to drain, and in turn current can flow from drain to source through this channel like this. Now we have got a channel formed by negative charge carriers here. Okay, so that creates a path between source and drain. Okay, that's the point cleared here. That forms a channel region here. Channel length is very important, as I mentioned earlier, which is 0.1 micrometer to 3 micrometer. That is the typical channel length. As I told you that the textbook that we are referring, Cedar Smith, is okay, which is a micrometer technology based textbook, but currently this has been changed to nanometer. And even width also you can see that in micrometer dimensions we have 0.2 micrometer to 100 micrometer. So this is the channel width W and channel length L here. Okay. So the MOSFET is a symmetrical device. Its a source and drain can be interchanged with no change in the device characteristics. Unlike the BJT is not a symmetrical device. Let me show you the structure and explain why this source and drain can be interchanged. So look at here, this source region which is an N plus region, and drain region is also an N plus region. We do equal doping for the source region and the drain region here. Many times it becomes difficult to identify which is source and which is drain. Though we are showing here the left side is the source region and the right side is the drain region here, but in physical MOSFET it becomes difficult because these two can be interchanged. That means you can make this as source or this as drain. It's possible because the doping is equal. These two terminals can be interchanged. But once you look into the circuits, you will understand that which is source and which is drain. Especially in NMOS, we connect drain to the positive voltage and source to the ground. That means the one which you connect to the ground becomes a source, the other one which you connect to the positive voltage becomes a drain, since these two terminals are interchangeable. Okay, I think with that we have covered the sufficient details with reference to the physical structure of the MOSFET. Let's move on to the physical operation. Okay, so before we discuss biasing circuits based on MOSFET, I try to make this physical operation as simple as possible. Anybody can understand the physical operation of MOSFET through these four steps. What are the 4 steps? Number 1 is, let's try to understand MOSFET without applying any gate voltage, with no gate voltage. Second is operating MOSFET by creating a channel for the current flow. We just create a channel. Okay, we will see what voltages creates a channel. Okay, and whether this creating a channel alone conducts current within the device or not, we will see that. Then later we will try to see the device when small amount of drain source voltage is applied. This is one case. Another case is when same drain source voltage magnitude is increased, what will happen within a device, we will see that. So in this way we have 4 different steps here to understand more about MOSFETs here. Let's try to understand the first step here, with operation with no gate voltage. That's the first step here. What happens when there is no gate voltage? Okay, when there is no gate voltage applied, no bias voltage is applied to the gate. In such case, we will see 2 back-to-back diodes that exist in series between the drain and source, like this. Okay, source region, which we said already, it is an N plus region, and the substrate, which is the P type, that forms a PN junction like this. And you can see drain region also, which is an N plus. Other side we have a substrate within the MOSFET. Just let me show you here with the physical structure. Okay, this device what I am talking here. Without applying any gate voltage, what happens? So let us see here now. So the type of device, diode that has formed here, let me highlight here, so you can see here. This is the PN junction which I am talking to you. This is one PN junction, another PN junction is here. Okay, So we are not applying any gate voltage here. So this voltage is Vg is made 0. So let me write here. So here gate source voltage, between this we make a short circuit. So this is VGS equals 0. Now what happens here, you can see that the substrate also is 0 potential, and this gate also it is 0 potential. These diodes here, PN junctions that we are seeing here, they are back to back connected diodes like this. Okay, this back to back connected diodes, and their operation is, that doesn't work. So okay, they remain off, turn off. Let me show here points that we cover here. Yeah, there are two back to back diodes I have shown that exist in series between the drain and source. Okay, these diodes prevent the current conduction from drain to source when a voltage VDS is applied. The path between the drain and source has a very high resistance, which is typically 10 to the power 12 ohms. What do we mean by that? So here, when we look at the physical structure here, when we try to apply a positive voltage here to make this device to conduct without applying gate source voltage, now if we try to apply a voltage here between the source and the drain, a positive drain source voltage, now you can see here positive is going to the cathode of a diode here, right? This complete region, now let us take it in terms of a PN junction, which is a cathode here. For a cathode we are applying positive voltage to the cathode here. That makes this PN junction reverse biased. So therefore this complete path becomes an inactive, this doesn't conduct at all. So the device remains in the half state here. So it's very important here, when we make VGS as 0, though we apply VDS here, the device remains in the half state. So that meaning of that is the drain current or drain to source current is going to be 0. So for VGS is equal to 0. The first step, I hope it is clear to all of you. Apply operation with no gate voltage. That means since the drain to source path has got very high resistance now, this makes drain current as 0 here. Okay. Any questions so far? The remaining 3 steps we will try to discuss, cover in the next class here. Okay, then we will immediately start with the MOSFET biasing here. At this point I would like to stop here. The other 3 steps of operations we will cover in the next class here. Okay.